I'm briefly going to talk today about really what's coming next for planetary astronomy. So I study small bodies in the outer solar system. But what I wanted to sort of touch on today was really touching on all of the bodies in the solar system and data that your students that you're teaching now will be playing with and studying and teasing apart if they study physics and go on to study astronomy in the next decade. And part of our jobs as astronomers and astrophysicists is to do the science now, but also to prepare the way for the next generation, right? And pushing to get the new technology and the new surveys online and ready to go. And so I'm going to be talking about the Vera Rubin Observatory and its legacy survey of space and time, which is going to be the largest astronomical data set ever generated that will take 10 years to obtain and will take decades more for the astrophysics community to unravel and understand. And so I thought that we always talk about in science about what we're doing now, but I thought I'd talk about what I've been doing to help prepare for this telescope and what are some of the interesting science that it will do. So why do we study bodies in the solar system? The main reason we do this is because they tell us about planet formation, right? We go from the image on the left, which is again sort of a planetesimal forming disk with gas where it formed planets around a new star. And that ultimately gives us something that looks like our solar system, and that we know 4,000 other solar systems around in our galaxy, but the best one we're ever going to study is our own. And so understanding the planetesimals is really important because they're the remnants left over from the formation of these objects. They're the bricks and mortar left over after the building is made, right? And by studying them, right, the building has weathered, right? These objects have changed, the planets change and evolve, but we can look at what the planetesimals can tell us about what they originally looked like, what the planets originally looked like, and how the solar system formed and evolved. So I want to highlight that this is a plots taken from the minor planets that are showing the current view of our inner and outer solar system. So on the left, we've got the inner solar system, and each of these sort of cyan circles are showing you the orbits of the terrestrial planets plus the orbit of Jupiter. So we've got, Mercury, Venus, Earth, Mars, and then you see that sea of green of material all about, and then that extra ellipse circle is the orbit of Jupiter. And all of those are mainly near-Earth asteroids or main belt asteroids that are orbiting between Mars and Jupiter. And so there's a lot of material sitting out there in these planetesimals, in these small bodies. And so on the right, I'm showing the outer solar system. And so this is about 4,000 known objects. This is more my area of study, orbiting beyond the orbit of Neptune. And so these objects make up typically what we call the Kuiper belt or the Kuiper belt Edgeworth belts or the Trans-Neptunian region, and Pluto is a member there. So again, one of those reasons why Pluto went home and why it was demoted is because it clearly fits in within the sea of planetesimals. Although it's the largest, it still fits in with the sea of planetesimals orbiting beyond Neptune that tell us about how the giant planets their cores formed, and how the solar system has evolved. So I just want to highlight again, solar system objects and small bodies are active or can be active. And so there's a whole suite of objects that are like our comets or active objects, as we say now in the solar system. And there's now a blurry line between whether you're a comet or just a planetesimal. And that, we have objects we see in the solar system that start outgassing and start sublimating ices. How do we find solar system objects? We go take an image of the sky. We come back a few hours later and we come back a few hours later and we look for the fuzzy blob that moved. And so this is just showing an image in the center here is Eris. It's the largest, or rather it's the most massive dwarf planet in the outer solar system. So it's round, but it looks just like any star in the image, but it's moving. And you might notice this blip here, that's actually a fast moving asteroid. So how fast these objects are moving in the sky can tell us about their orbit and their distances. Their light can tell us about in different colors, and how much light they're giving off in different filters can tell us about composition. How the light changes over time from these objects can tell us about its rotation and its shape. And so there's a lot we can learn about these solar system objects and try to tease out the history of the solar system. And so what I've been spending a good portion of my time doing is helping prepare for the Vera Rubin Observatory and the Legacy Survey of Space and Time. So this is going to be the biggest, public data set ever generated from a telescope. Each night it will generate 15 terabytes of data nightly of image data. I don't even know quite how to put that into ways I can understand, but it's basically taking 15 of my laptops, right, and producing that each night. And so this telescope is being built in Chile. It's about an 8-meter telescope, and it's being built now, and operations is expected to start in 2024. And so the UK is playing one of the roles in here as part of that survey, and helping to, the community in the UK is really interested in using the science and the observations that will come out of Rubin Observatory. And I just want to highlight that Rubin Observatory is not just only going to do solar system science, but it's also going to probe dark matter. It's going to map the our galaxy, the Milky Way. It's going to explore the transient night sky. So anything that goes bump in the night or explodes. And so this telescope will survey the night sky every 3 nights. The entire visible night sky from Chile will be imaged, repeat, every 3 nights, in multiple different filters to get us colors. And so it's effectively making a movie of the night sky every 3 nights. And so this is going to transform how we do science. And just to give you some scale, you know, we show you all these things that are completed, but this is showing for the first time the telescope actually moving, installed in Chile, rotating for the first time under by hand by the technicians that are installing the telescope. But this shows the observatory. This is on Cerro Pachón in Chile, and there the telescope is being moved by hand. But this is the first time it was the view of it being fully assembled and starting to move, although not by its own motors yet. And so this telescope is going to be quick, fast in the sky. It is the cutting edge of astronomical technology, imaging technology. Now, there's no mirror in the back end of this yet, but this is still in construction. And so I wanted to highlight and show you some of the sort of, you know, what this looks like, because we always show you the data, but we never sort of show you the process of getting to building the observatory. And so this has been many years in the making, right, to be able to get to the point of even having a dome and a telescope in it, zooming around. And behind this, you know, massive telescope and its mirror, when it eventually gets put in, will be the LSST camera, and this will be it'll be 3,200 megapixels. So this showing you on the left the camera, and on the right is Romesco broccoli imaged by the camera. It's the largest field of view camera ever built in astronomy. It has way more pixels than your phone or my phone camera. And this is what's going to generate, you know, these images, or the 15 terabytes of data. And I should say is that this is going to this field of view covers 40 times the size of the full moon, just to give you some scale of how much wide field coverage we can get in a single image from this observatory. And so for the solar system, why I'm excited about this, and why, you know, I think sometimes we forget to tell students about what's coming online that they will get to potentially work with, the data that will be coming down the line, is that Rubin Observatory and the Legacy Survey of Space and Time will find an order of magnitude more solar system objects that exist today that we know of, effectively, that we've discovered before. And so it's going to unveil this hidden solar system that we've never been able to see because we couldn't probe deep or wide enough to see these objects. And so we're going to go from 650,000 asteroids to 6 million. For outer solar system, we know about 4,000 known outer solar system objects today. We're going to go to 40,000. I don't even have a good visual to give you for this because it's such a huge number. And with that becomes an ability to really tease out the history of Neptune's migration, or how the giant planets formed, how the solar system has evolved, and how it is evolving today. Because we're going to have this movie every 3 nights. We're going to have this new movie of the solar system, right? And so every object that's active, right, that is outgassing, we're going to be able to find if we can see it with Rubin Observatory. And we'll see its change in brightness, or we'll see it has a fuzzy tail. And so this transforms planetary astronomy in so many different ways, because it provides such a rich data set to really tease out the history. And so we've had broad strokes from what we've been able to do now in putting a picture of the formation and evolution of the history of the solar system and its history. But now we're going to get really into putting the puzzle pieces fully into place. And I think that's what's exciting. And so the survey is going to turn on in 2024, and there's so much more that we can learn. And I'll highlight in the last 30 seconds or minute I have is just that interesting things we'll be able to do is look at main belt asteroids that behave like comets. There seems to be an orientation that the ones that sort of repeat an activity that might suggest there's ice on their surface somewhere hidden, which we wouldn't fully expect, is somehow aligned with Jupiter. We don't know why, but finding more of these objects, because they're needle in the haystacks, but by having so many asteroids, we'll be able to find more to fully understand this. There's models that suggest there's a 9th planet orbiting way beyond Neptune. but there's a lot of debate in the community whether this exists. And Rubin Observatory will either find it, directly detecting it, or it's going to find all these objects that seem to be oriented in a way that suggests there's this planet 9. We'll be able to actually test that by looking at these objects of these orbits further out and seeing if there's any more or if it's different from what other people have been able to find. And lastly, just to say that there's interstellar objects. These are objects from other solar systems that have been ejected from theirs and are passing through our own solar system. And so these objects will tell us really interesting things about planet formation in other solar systems, but they're coming into ours, right, temporarily falling in. And so we'll be able to basically use the same techniques we use to study our own solar system small bodies on these objects. And we only know of 2 interstellar objects to date, but Rubin Observatory is going to find at least, we think, 10 a year. So completely transforming sort of how we understand how other solar systems formed by comparing their building blocks to ours. And I'll just highlight that the ESA's Comet Interceptor mission is being led through the UK, and that Rubin Observatory is going to find the comet that this mission goes to. So this is the first mission to be launched without knowing where it's going. So it's going to fly by a new comet that's coming in towards our solar system or an interstellar object. And to do that, right, we need to sit and wait for this comet to get close enough. But we don't know of a comet yet that we could send this mission to. So when the mission launches in 2028, it'll sit and wait. And when Rubin Observatory finds a comet that it can go to, it will set a trajectory and off it will go. So I think that's the exciting thing within the UK of having a UK-led mission, and people like me and other people on the team that will be helping to find the target that we will send Comet Interceptor to through Rubin Observatory. So that's all I really have to say, and just highlight that it's coming, right? This data starts flowing in 2024, and that, you know, this is the data set that, you know, this is the telescope that astronomers, you know, will be spending the next several decades going through to study the solar system.